right, so welcome everyone to this first session of the ONEPAS Thematic Series. This one entitled The PDEs of Quantum Mechanics, and it's curated by Michael Sigal. So it's a real pleasure to introduce Michael Sigal indeed for this first overview talk of the series. Thank you very much, everyone. Thank you, Michael.
Okay, thank you very much, Fabio, for introduction, and I would like to thank the organizers for giving me this opportunity to bring out some of the recent and not so recent work in mathematical physics related to the partial differential equations. So I will, my talk will be directed to the people who are practitioners of the partial differential equations, people who do partial differential equations, but hopefully it will be also useful for mathematical physicists, though the origin of the subject matter comes from mathematical physics. So here, let me explain this blue matrix here. Is rows are listed in alphabetical order here, but the columns are in a somewhat chronological or according to the chronological order or according to the length of our collaboration. So probably I was collaborated most with the people in the first row, and then it goes down, and hopefully we will catch up with the last row. I hope we'll have more work together. And there is this discussions with Rupert Frank and Christian Heinzel, with whom we did not collaborate, but I benefited from discussions with them a lot. Okay, and something else I wanted to say, but I forgot. So let me see. Now let's see how. Okay, so this works only through the maps. Okay, so I will start with the kind of a mother of all quantum equations, is the many-body Schrodinger equation. So it's written here in the first equation here. So all information about quantum systems, such as atoms, molecules, solids, and nuclei, stars, are contained in this equation, where H sub n is a differential operator written here. So it's a sum of Laplacians, which describe kinetic energy of the particles plus interparticle interactions. So to not clutter the slide, I did not write external potentials, for example, and I assume that all particles are identical. So we have the same mass and the same kinetic potential energies, but it could be very different. So in fact, the results which I will report in the next slide is not sensitive to this. So as I mentioned, n is a number of particles, masses, m is a mass of a single particle, and they interact via two-body potential. V, again, this is the fact that it's two-body, it's a natural assumption, but would not be that important. Now, global existence. So from PDE point of view, first of all, you would like to understand the global existence for this equation. And this turns out to be rather simple. So global existence, you have a global existence for this equation if and only if Hn is a self-adjoint operator. That's it. So in one shot, you can describe, you can show that all the quantum systems occurring in nature, in fact, are self-adjoint. There could be, of course, very special cases, super singular potentials, but this comes more from modeling than from the natural assumptions. Now, here is here we start. Here's the second difference with the usual PDE problems, is that the goal here is to describe a space-time behavior of solutions. In other words, we want to address the problem of stability versus decay. Stability is localization in space. It's like and periodicity in time. It's like atoms, molecules, and so forth. Right? It's definitely well localized object, and that's what we mean by stability. While decay could come from two sources. First of all, it could come from collapse. Well, by decay, I mean, I could mean in principle collapse, which means that in terms of the operator, Schrodinger operator H sub n, we have a lower, to show that there is no collapse, we have to prove a lower bound on this operator. And this is, here again, we can go in two different directions. So this will be collapse again. So this will be stability against collapse to a point. But you also want the stability with respect to the size of the system. You want a system to be the size of the system to be proportional to the number of particles involved, which means in this context, it means that this constant should be proportional to the number of particles. Okay, so this goes under the name of stability of matter. This is the second type of stability, which I will not touch upon here. The second type of stability is stability with respect to the breakup. So by this I mean mathematically or spectrally, it means that the gap between the lowest eigenvalue of Schrodinger operator and the rest of the spectrum is positive. In other words, lowest eigenvalue is isolated. Lowest eigenvalue is lowest point of the spectrum is an isolated eigenvalue. This will tell us that the system does not break in the lowest energy state, does not break into the clusters, into fragment. Okay, and okay, once we have talked about this breakup, we can do a bit, we can refine it. So first of all, by breakup, I would mean that it's a local decay. So if is the center of mass of the system fixed, then it breaks into fragments which fly away from each other. And so further on, you can okay, this is local decay, and then so this will imply more precise statement about how the breakup takes place. And then finally, we have a scattering problem with the scattering. So the system breaks into the fragments, and then fragments move independently independently and as a free kind of clusters away from each other. And this will be a scattering problem. Okay, so the first result I would like to mention is, so in this talk, I will not give the references inside of the talk, but I will collect them all at the very end, so not to interrupt myself. So the first result is establishing kind of a propagation cone for this Schrodinger equation. So propagation cone is well known for the wave equation and similar equations, and but apparently it also exists for the Schrodinger equation, which is known to have infinite speed of propagation. So what do we mean by this is exactly what's stated in this theorem, is that if the energy is localized in some interval I, so this will be G of H, where G is a C0 infinity function. And if C is a constant which is greater than, this is the momentum, absolute value of momentum operator times this energy cutoff with interval I, then under very general assumption on H, we have the following bound. The solution of the Schrodinger equation outside of the ball of radius C times T, decays with arbitrary small power, provided it's localized initially. And similar results holds for the minimal propagation speed. So then you have to show that X, the probability for X to be less than some other constant times T decays with arbitrary power. But with this is with the maximal velocity estimate here, replaced by this one. And this is much more delicate result. So the maximal propagation speed bound here, maximal bound of propagation. So the potential, the operators here could be of very general nature. We don't require smoothness of, it could, smoothness of the potentials or the decayed infinity or many body structure, the potentials could be random in principle. Still, you have propagation, you have a bound on maximal velocity of propagation. For the minimal velocity, of course, this is not true, right? So if you have a random potential, it will not propagate as a rule. Say in one dimension, for example. So you need more structure. And in that here, n-body structure usually suffices. Okay, so this bound 2 implies that probability to be outside of this ball of radius CT, probability to find the system outside of this ball, the case with the time as inverse power of time. And the version of this result implies a limitation of speed of propagation of information. It takes at least rho over c units of time for a signal originating at the origin to reach region where x is greater than rho.
So
Okay.
let me interrupt. There's a question in chat that I'd like to relay. So the question from chat is, can you explain the infinite propagation speed of the Schrodinger equation? And then the follow-up is, perhaps this was misheard. I guess the question is, did you say that there was infinite propagation, or?
Well, we think about Schrodinger equation of having infinite speed of propagation in the sense that if you take a localized initial condition, localized in a ball of radius 1, then at arbitrary positive time, solution is non-zero everywhere, unlike with the wave equation. However, if you say, I don't care about solution being 0, I only care about solution being less than 10 to the power minus 10, right? Then you have a speed of propagation if you have a cutoff on the energy. If you don't have a cutoff on an energy, if energy distribution of initial condition is arbitrarily large, then you don't have this bound on the speed of propagation. Okay, but I can answer more questions later. So okay, now I want to talk a bit about scattering. So the main mathematical problem of the scattering theory is asymptotic completeness, and it states that as time progresses, the quantum system settles in a superposition of states, each of which is broken into a stable, freely moving fragments. Right? So each of these states is called quantum channel. And since it's quantum mechanics, if you have one possibility, you have superposition of several possibilities, you have superposition of these possibilities, right? Unlike classical mechanics, you don't have to be in a single channel, you can be with some probability in the different channels. And the asymptotic completeness states that suppose that the pair potentials, now I assume that particles are different particles, entering our Schrodinger operator satisfy decayed infinity fast like y to the power minus mu, with the mu greater and equal than, strictly greater than square root of 3 minus 1. Then asymptotic completeness holds. The open problem is to show that it also holds for mu less or equal than square root of 3 minus 1. Square root of 3 is the natural threshold. So you essentially have to understand, say, if you look at the three-body problem, then for long range potentials, then it's reduced to the one-body problem with the time-dependent potentials. And so you don't have restrictions on an energy anymore because potentials depend on time, energy is not conserved. And what you have to understand is you have to understand diffusion of quantum particles with a near zero energies. And that's where this bound come from. So for mu greater than square root of 3 minus 1, you can control this. So you look at the kind of a macrolocal analysis, but with not in the cones, but in a deformed cones, parabolic cones, right?
Michael?
Yes.
Just a question. The root 3 minus 1, Is it in 3 dimensions? Is it dimensionally dependent here?
No, it's not. It's not dependent on dimension.
Okay.
Right.
Thanks.
So 3 here is not a dimension. So let's. In fact, the main result in the notion of the long range, short range scattering is dimension independent. Okay, so now I want to go to the quantum electrodynamics. So I mentioned that I began my talk saying that all quantum systems, all properties of quantum systems are described by the Schrodinger equation, but I should have added a caveat. As long as we don't see it, as long as there's no photons in the system, as long as there's no electromagnetic waves. Now I want to include the photons. So so then again I have again Schrodinger operator. Now assume that my electromagnetic field is classical. Then this will be this is what's called minimal coupling. So I replace my momentum by covariant momentum, by covariant derivative, right? Think about this as a connection. And I add also the Hamiltonian for the photons. So it's integral of E square plus B square. Integral of the square of the electric field plus the square of the magnetic field. The only thing is that we have to quantize it. Because to understand radiation, you cannot understand radiation in a semi-classical, in a quasi-classical way. You have to have photons must be, electromagnetic field must be quantized. Right? So I will not describe this could be a separate maybe series of talks, how to quantize electromagnetic field, but it can be quantized. You can so in quantization you will think about vector potential, magnetic potential as a multiplication operator on some L2 on a space L2 space over Schwartz distributions, for example, and the electric field as a let's say Frechet derivative on this space with respect to this potential, this multiplication operator. So this will be replacing coordinate x and p, coordinate momentum. So electric field will play a role of momentum and the vector potential. It's important to have a vector potential will play a role of coordinate. This is the difference between classical and quantum mechanics. Right? In classical mechanics, vector potential, magnetic potential, the same as electric potential, play subsidiary role. It's just to reduce number of equations. You can forget about it. Not in quantum mechanics. I cannot couple my quantum particles to the electromagnetic field without potential, vector potential. That's how the coupling goes. So okay, so this is a vector potential. C is ultraviolet regularization, and HF is Hamiltonian for the photons. So main problem here is an infrared problem. So I assume that, for example, by ultraviolet regularization, I cut off my say vector potential at the energies, let's say, of the order of the mass of the universe, right? So it doesn't have to be unbounded. So in fact, I cut it, of course, on much lower scale, but in principle, I can cut it on very high scale. Then so our problem is infrared problem. What's infrared problem? Infrared problem comes from the fact that photons are massless particles. So in other words, very arbitrary small fluctuation, energy fluctuation. So we have uncertainty principle between energy and time, and arbitrary small fluctuation of energy could generate infinite number of photons. So what happens is that every particle, electron or proton or neutron, is surrounded by a cloud of fluctuating photons, virtual, which come from the vacuum and go back to the vacuum, and with no limit on the number. It could be infinite number, and it's always non-conserved. There is no conservation law for photons. They are emitted and absorbed constantly by a matter. They interact strongly with a matter. So the main questions here are emission and absorption of electromagnetic radiation. So we want to understand how the photons are produced by matter, mass renormalization. It means that your electron is surrounded by a cloud of photons and becomes heavier. So its mass in fact is not the same as initial what you think the mass would be without electromagnetic field. And then the third problem is a problem of the scattering problem, which is similar to the one I mentioned before. So I cannot address these two problems because this requires lots of machinery definitions. But here, this also requires definition, but I can say words here.
Michael?
Assume that we have the following bound in the number of photons. So there's operator. So think about operators as the random variables. There's an average of there's operator of number of photons, and there's average in the solution of the Schrodinger equation. Right? This is average of this observable of the number of photons, and assume it's uniformly bounded in time. Then the symptotic completeness holds. Now this bound was proven by Deroik and Kopianin for finite dimensional quantum system, not the quantum system like this one, but if you replace the quantum particle by finite dimensional particle. So this is a major open problem. It's very simple to formulate. So show that you have this uniform bound here for general particle system. So you have solution of the Schrodinger equation, then define a number of photon operators. So if it acts on a wave function with 5 photons, it's equal to 5. If it's 10 photons, it's equal to 10 and so forth. But you can give it also analytical expression in terms of the so-called quantum fields or creation and annihilation operators, right? And show that this is constant. So this is open problem. This is at the core of lots of different issues.
Michael, sorry, maybe still about the infrared problem. There is a question about where does the energy of the infinite number of possibly infinite or unbounded number of photons come when they're emitted? Where does the energy of the unlimited emitted photons come from?
Energy of emitted photons.
Yes. And how come there are infinitely many or potentially infinitely many? Okay,
so energy of photons is here. So this operator acts on so-called Fock space. So Fock space is direct sum of n photon spaces, direct sum over n. So it's well-defined operator. There's no bound on the number of the photons, right? It can be arbitrary, but this is well-defined operator. Its energy could be, of course, infinite. So if you take an average of HF in the state psi sub t, in principle, it could be infinite. Right? So you check. The thing is that if you take the initial condition with the finite energy, then you want to prove that the energy will be finite for all times. And you want to prove that also energy will not grow with the time. So this can be done. Actually, this bound on energy can be done. The bound on the number of particles is more difficult. Okay. And the reason is that energy has Einstein dispersion law. So this Einstein dispersion law is in kind of a pseudo-differential notation is absolute value of xi, right? It's absolute value of the gradient sitting there. It's a square root of the wave equation. So, and this helps because it dampens the energy of very soft, it's called soft photons with a tiny energies, because they are dangerous, because you can have infinite number of them. Okay? Can I continue?
Yes, please.
Okay, so now I want to come to the effective equations, equations of quantum physics. So this was, Schrodinger equation was, I don't want to say God-given. So I was brought up in Marxist religion. So I should given, it was given by the, so what will Marx will say by the electric materialism, by the scientific development of the world. I don't know what's the right expression. It never, Lenin had a paper about article about the atoms, but about electrons, but not Marx. So I don't know exactly. So anyways, so but these equations are so Schrodinger equation is like a Newton's equation in the classical physics. And this will be like Boltzmann or Navier-Stokes or Euler equations, right? So this is effective equations. So we want to look at now. We want to look at this approximate equations where we can understand the solutions much better, behavior much better. So I'll be looking at a system of n identical bosons or fermions, whichever this means. And with this, they are again described by the Schrodinger equation. The difference between bosons and fermions is that for bosons, the psi should be symmetric functions with respect to permutation of the particle coordinates, and for fermions, it's antisymmetric with proviso or changes according to certain two-column Young tableau. So to obtain the way one obtains effective description of such system is that for large n is to, and here particle could be an atom or a molecule. It doesn't have to be electron. Is to restrict this equation to the either symmetric product of a single wave function, single psi, depending on our single particle coordinate, or antisymmetric product of n functions, L2 functions. So in first case you get the Hartree equation, and in the second case we get the Hartree-Fock equations, which is mainstay of the physics and chemistry, quantum physics and quantum chemistry. And so I will come to them later, but I would like to address. I would like to introduce a little bit more general equations, and since these Hartree equations, Hartree-Fock equations, fail to describe quantum fluids, so such as superconductors, superfluids, or Bose-Einstein condensate. For this, one needs another conceptual step. So the derivation of the effective equation is it's a big area in mathematical physics. So I will not touch upon this. So there is lots of rigorous results. Definitely, Hartree-Fock equations are derived rigorously, but equations which I will describe in a moment do not have a full, complete, rigorous definition. However, what I want to do, I want to give some kind of intuition how they arise. And here is I want to discuss this a new conceptual step to bring it, to motivate this step. I want to reformulate my problem as follows. I want to think about Hartree-Fock equations or states as non-abelian generalization of random Gaussian fields. So the latter, such Gaussian fields are uniquely determined by 2-point correlations, assuming you centralize them to the zero average mean. And so we want to generalize this to the quantum fields. Again, centralized quantum fields, by assuming that the latter are uniquely characterized by quantum two-point correlations. So here's this usual average, mean average for your random fields, but here is the average in a state of the quantum system, right? Where psi hat and psi hat is the quantum field. Whatever this means, it means, okay, it means it's space value, it's operator valued functions. In fact, distributions, to be honest, but we don't care about this for the moment. It's operator valued functions. So you replace functions by operator valued, non-commutative operator valued functions. And if you do that, you will get exactly Hartree-Fock states. So that's another way to account to the Hartree-Fock states, to look at the all states which are described, which are completely described by two-point functions. So if this is the Hartree-Fock state, then the operator gamma with this integral kernel here will satisfies the Hartree-Fock equation. And here I wrote the Hartree-Fock equation in density operator form, not maybe standard form, but the form of density operators. So if you take an operator gamma with this integral kernel, then it will satisfy equation ID gamma dt, commutator of H sub gamma with a gamma, where H sub gamma is minus Laplacian plus some interaction here, self-interaction here, which I don't write down. It's called exchange correlation or whatever. Some interaction depending on gamma. Right? It's nonlinear. Now we have nonlinear equation. So just a little aside here is that the density functional, in the density functional theory, so, which is has incredible success in physics and chemistry. In fact, all the computations in physics and chemistry with the quantum gases or fluids are done in the framework of or atoms and molecules, but biological molecules are done using the density functional theory. So here you replace function of gamma of operator by function of a function of a density of gamma, where rho sub gamma of x and t is the putting gamma on a diagonal. It's a diagonal of gamma. And this very simple kind of a simple approximation, in fact, gives it turns out to be extremely efficient in computations. Okay, so let me go on. So now so this is not yet the new concept. So this is just motivating the new concept. But now I come to the extra step. So states described above are not the most general ones which are determined by the two-point correlations. The most general ones are defined by all two-point correlations, which includes also psi hat with a psi hat, not a psi star with a psi, but psi hat with a psi star, which in the Hartree-Fock theory, this one alpha will be 0. So alpha describes microscopic pair coherence, pair wave functions. In other words, it's not just a product of a single functions, but also brings information about the pairs. So these types of states were introduced by Barton Cooper Schrieffer for fermions and Bogoliubov for bosons. In fact, if one asks what is a new mathematical insight for which Barton Cooper Schrieffer got a Nobel Prize and for which Bogoliubov should have gotten the Nobel Prize, from their work on superconductivity, this was this one. That was the new step. If this is the entire, you can think that the entire kind of new mathematical structure of superconductivity comes from this step compared to the normal fluids. Right? Okay, so now we have two functions, gamma of x and y and t and alpha x and y and t. We can associate with them two operators if you wish. And so that will be our new states described by, instead of a gamma, by pair gamma and alpha. Okay, so for such states, all correlations are either 0 or sums of products of quadratic ones. And this is kind of a weak, okay, it's not a weak, it's a weak. So it's Italian mathematician. Weak property comes from quantum field. So it's well known in quantum field theory, and we'll call them weak states. So, so they give the most general one-body approximation, or essentially one body, but with a two-body input approximation to the n-body dynamics. And now we can write the, okay, we have to have dynamics with these weak states. Okay, this, I don't kind of expect people to really follow this, slide. Maybe what I want to convey is some kind of impressions. Is impressionistic. Think about this as a painting. So we don't have to understand it, but we have to feel it somehow. So let me write now this average at the time t as a omega sub t of A. Right? So this is my quantum state, omega sub t. So I gave it a letter rather than kind of broken braces. So now I reformulate the Schrodinger equation as equation written here. So this is equivalent if H is well, in general is operator on a Fock space, but if you restrict to the fixed number of particles, this equation 7 will be equivalent to our original Schrodinger equation, where A is arbitrary observable. So arbitrary operator on our state space, on Hilbert space on which equation is defined. Now I'll define the weak reduction. So I want to have approximation for solution of this step. I want to make this equation into the equation for weak states. Right? And on the first side, I didn't do anything. I just write exactly this equation here. Just change omega to phi. Phi state will stand for, well, for the weak state. It should be W. And so it mathematically is known as the quasi-free state. So that's where that comes from, the phi comes. But I restrict the observables. So now observables will be quadratic in the quantum fields, in the creation and annihilation operators, in the quantum fields. So I can look at the quadratic quantum fields or quantum fields of this form, or quantum fields of this form, or single ones, but I will not go to higher ones. So if I start with if I look at this equation and initial condition is a weak state, the solution is not a weak state, never is a weak state. However, in this case, the solution will stay again in weak state if I restrict everything to the quadratic observables. So observable is just operator on the state space. And this yields a system. This you can translate as a system of coupled equations. So first you evaluate this on this product, and then you evaluate it on this product, and you have equation for gamma and alpha. Right? And if you evaluate on a single one, you have also equation for the singleton. Right? So for bosons, these are Bogoliubov-Dejean equations, and for fermions is Bogoliubov-Dejean equations, and for bosons is Hartree-Fock-Bogoliubov equation. So the idea in a pure form, the idea was right. So Barton Cooper Schreiber, who got I want to say Fields Medal, who got Nobel Prize, never wrote equations. They had a formulation equivalent formulation of this theory in terms of the field Hamiltonians. Right? So equations was first written by Bogoliubov of this type. right? And then explained and reformulated by Degeneracy for fermions well, since they come from Hartree-Fock, it's called Hartree-Fock-Bogoliubov for bosons. Anyway, so BDG equation, Bogoliubov-Degeneracy equations, given, as I mentioned before, give an equivalent formulation of BCS theory, Bardeen-Cooper-Schrieffer theory of superconductivity. Okay, now I write out this equation. So let me repeat what I said before. So for bosons, a weak state satisfies this equation as before. For at most quadratic observables, now we introduce, first of all, average. So average in the state phi sub t of the, I remove heads now, of the field operator itself, singleton here. And this we'll call phi. Somehow something happened and doesn't want to underline anymore. Okay, here. Okay, phi. And then we do similarly for quadratic terms, psi star and psi, and we get gamma and alpha, functions gamma and alpha, and then with the gamma with the shade, this function with shade operator gamma, and with this function operator alpha. So we'll have a triple, phi, gamma, and alpha. And this will be, and this triple will satisfy Hartree-Fock-Bogoliubov equations, but I will neglect, for simplicity, I will neglect alpha component. It doesn't play a big role here, only if it's super fluidity component, which for what I will be talking about, it doesn't play a role. And I will replace V by delta, multiple of delta function, just not to write V. V is an interparticle potential. Right? Then I have this system of two equations, the so-called neglecting alpha leads us to two gas model. So this is Hamiltonian system. So the first equation, if you forget about last two terms, last term, the blue term, is just Gross-Pitayevsky equation, or a linear Schrodinger equation, if you wish. Right? Where H is minus the plus and plus V, where V is external potential, which are now introduced. Now, the second equation is the Hartree-Fock equation. And they're coupled this way. They're coupled through this term, right, which involves both gamma and phi, and coupled through this term, which H of gamma phi is the H plus, okay, so rho gamma is again, it's the gamma on the diagonal. So this part, so the first two terms, is exactly the operator which enters into the, well, up to the 2, of course, up to the 2, which enters into Gross-Pitayevsky equation, and then you have a coupling here. No, sorry, this is Gross-Pitayevsky equation, and this coupling to the gamma equation. So we have two equations coupled. Right? With two fluids or two gases or two liquids coupled together. So this is Bose-Einstein condensate. It's a wave function of Bose-Einstein condensate, and gamma is a density operator for non-condensed atoms. In fact, no, the Bose-Einstein condensate does not, to produce Bose-Einstein condensate, you have to have non-condensed atoms. You cannot have them because the way it's produced, you put it in a laser, in a trap, in a laser beam, and then you take out, evaporate energetic atoms. So you have to have reservoir to which you can throw out the atoms which energy is higher than some energy. So you need this. So this is the natural system. So this is, again, as I mentioned, a couple Gross-Pitayevsky and Hartree-Fock equations. And here we can talk about natural problems we address in partial differential equations. Its existence, ground state for it, condensation. Condensation is relaxation to the ground state, collapse oscillation. So here, what I mean by this is that in case lambda can be either positive or negative. So if lambda is negative, then it will be focused in a linear Schrodinger equation. In 2 dimension, it's mass critical, and there is a critical mass above which it starts collapsing. What happens is that if you don't have thermal atoms, this will collapse. And you will have this law of collapse was given by Papanicolaou Soulom profile. However, because of thermal atoms, what will happen is when it starts collapsing, it's like physicists say it's condensate heats up. And the condensate atoms from condensate evaporate into the thermal cloud, the non-condensed cloud, thermal cloud, and collapse stops. So you go a little bit further on, so it doesn't stop exactly at this stuff, and then it starts collapsing again and so forth. You have certain oscillations. So there is a numerical simulations. Nobody knows what's really, whether it's at the end it collapses or in the end it kind of arises some universal profile. So this is, besides of the numerical oscillations for finite time intervals, there's no results here. And again, set up here external potentials versus translation invariance. Now I want to describe Global-Degeneracy equation. I think that I'm running a bit late. Okay. So here, so this equation for fermions. So as a result, the phi will be equal to 0, and we have, because it describes superconductors, we have to couple this to the electromagnetic field. So these equations for operators gamma, alpha, and A are written here, and A is a vector potential. We assume the gauge such that the electrical potential is equal to 0. So if you look at this equation, you will see that this is equation for the density operator. This is minus stands for some kind of for the commutator, and plus for anti-commutator. This alpha is not a density operator anymore. You have to think about alpha as the wave function of the Cooper pair, so superconducting electrons. J is superconducting current, and H is before is the Schrodinger operator with a self-interaction piece. Right? So this is the celebrated Global-Degeneracy equations, which enter every book, well, most of the books on condensed matter physics or solid state physics or superconductivity. So I want to now stay on this equation a little bit longer and explain somewhat about properties of these equations. So first of all, if magnetic field is not equal to 0, if electromagnetic field A is not vector potential is not trivial, right? Then system is not translational invariant. Before that, system is translation invariant. Now system is not translation invariant. So one has to understand the system, to understand this equation, one has to notice that this is a gauge system. So in other words, we have a gauge invariance. And the gauge transformation here is standard for the density operators. And here is a transformation for two particle wave functions, and this is a standard transformation for the vector potential. So the simplest class of states are translation invariant states for A is equal to 0 when there is no electromagnetic field, and gauge translation invariant for A is not equal to 0, which means that translation would take you not to the same state, but to the gauge equivalent state, right? Because now the states are broken into gauge equivalent classes. Physically are not states related, solutions related by gauge transformations, physically are not distinguishable. So we arrive to the natural notion of gauge translational invariant states. So states which invariant under both. If you do translation by some vector S, right, of the state, and then you say, okay, the resultant translation is in the same gauge gauge equivalence class. So you can undo this by some gauge transformation. This. For 2 dimensions, which will the most relevant to the superconductivity. So we take this chi sub s can be given explicitly. It's the usual vector potential for the constant magnetic field. So again, here is H sub T sub S translation is a group of translations. B is a parameter which can be identified. So entering here, so identified with a constant external magnetic field. So I didn't introduce any constant external magnetic field, but this parameter naturally comes from the symmetry, from classification of solutions. Now,
Michael, sorry, I just see that we're going towards the end of the hour and that you have a lot more slides.
Yes.
So is there a nice time to at least stop and see if there are some questions? And then this is recorded. So if, I don't know if Ian can stay, but if you want, we can stay a bit longer after, but people, I mean, it's easy for people to—
No, I understand. So let me figure out what's the, in principle, I can make this, let me see what's the next. Yeah, okay, so let me make this as a last slide and then we'll see what happens. Okay.
Good.
Okay, so the main question, so here again, system without magnetic field, without electromagnetic field, system is translation invariant. So you want to look with electromagnetic field is gauge translation invariant. So the main question here is existence and stability of the ground state of the eigenfunction with the lowest local energy. So energy of the solution will be infinite. Solutions which have this invariance will be infinite. So, but locally we can minimize energy locally. Okay. So usually in physics, ground state, I will abbreviate it as GS, has a maximal symmetry. So depending on magnetic field B, one expects it to be translation invariant when B is equal to 0, or magnetically or gauge translation invariant when B is not equal to 0. Then the candidates for the ground states are normal states, where alpha is equal to 0, where there's no this extra term alpha, which comes from, as you remember, from kind of a superconductivity. In this case, gamma is so-called Gibbs state. For superconducting states, in this case, A is equal to 0, is Meissner state. States where magnetic field is expelled from superconductor, but alpha is not equal to 0. There's a theorem by Hansel, that's the only reference I made in the text, by Hansel, Hamza, Zinger, and Soloway, saying that for B is equal to 0, electromagnetic field is equal to 0, there exists a superconducting, there's a normal, and there was superconducting, and a normal in the sense that alpha is equal to 0. Normal translation invariant solutions. Okay, so this can be reconciled. So for B is equal to 0, we don't have to have alpha is not equal to 0 to have superconductivity. And here's the result by Elias Chen and myself, is saying that if B is equal to 0, then magnetically or gauge translation invariance implies normality. In other words, alpha is equal to 0. So superconducting states must break symmetry, cannot be magnetically translation invariant. Okay, so let me now skip to the last slide. Okay, so that's the summary of this talk, maybe without a few. So in this talk, I reviewed some basic properties of the Schrodinger equation, which encodes the information about quantum systems. While we learned a lot about general structure of this equation, our understanding of specific quantum systems with a number of particles greater or equal than 3 is spotty, and progress with a notable exception like stability of matter is very slow. However, there is one important direction where robust progress is possible, is effective equations. Okay, so I should not have this one. For quantum systems of large number of identical particles, especially superconductors, superfluids, and Bose-Einstein condensates, or Hartree-Fock-Bogoliubov and Bogoliubov-Degeneracy equations. So with electronic, and this is now I'll start prophesizing a little bit. So with electronic devices hitting the wall at the atomic scales, and with the growing use of quantum processes in leading edge technologies, research in PDEs in quantum mechanics is set to accelerate dramatically. And this will be it. Thank you for your attention. I'm sorry I ran over time.
Thanks a lot, Michael. I guess, do I lead the question sessions? Yeah.
But first, we need to be all muted and unmuted, no?
Oh, yeah. Who does that, Ian? Right.
Ian?
Or I can just ask questions.
Okay, as a reminder, in order to give you the right to unmute yourselves, I have to mute everyone. So in particular, Michael, you've been muted. Please unmute yourself.
You did not yet, right? So Michael, you're muted. You were muted for this.
There we go.
Yeah. Right, so are there questions for Michael?
There were lots of questions during the talk. So.
Besides what else is in the slides that we had to skip, but maybe we can ask about that.
Well, maybe actually we can.
One of the last one slide before the last gate varies. Here's the credits, which I skipped in the talk. So the red, actually in the red are the authors of the theories which were mentioned in the talk. And so I didn't talk about radiation, so there was lots of work on quantum radiation, QED. So ground states and the radiation states. And so I did, this would require quite a lot of definitions. Not definitions, but one needs some background in the quantum field theory. So this is skip, so there's no red here. So asymptotic completeness was joint work with Jeremy Fupa, and maximum velocity bound is recent work with Jack Arbonish and Fabio here, Avi Sofer, and myself, and so forth. So this is these two theorems were supposed to be in the last few slides here, but this was for another stability of vortex lattices and existence of vortex lattices for Bogoliubov-Degeneracy equations. But this was for another time, so this can be skipped.
Did you have a question, Benoit, or I also go ahead?
Michael, so I just had one question. So in your talk, you presented the Hamiltonian with a general two-body potential,
Right.
but then you specified to the Dirac mass as the direction. How much of an assumption is it, or will all the technique extend to more general potentials?
So there's no, actually there's no rigorous results for Dirac mass. Okay. So you can arrive to these equations by taking limits. You don't put in Dirac mass into the n-body system, but you take a certain limit. For example, assume you have an n-body system. Assume we are talking about Gross-Pitayevsky, excuse me, about Gross-Pitayevsky equation. If you notice in Gross-Pitayevsky equation, the potential is a Dirac mass. It's a Dirac wave function, right? So you take a special limit, it's called gross Pitayevsky limit, where the potentials is rescaled in such a way that and replaced by scattering T matrix. So in other words, you do massaging equation quite a lot, or you do perturbation theory and you resum some diagrams if you wish. Massaging equation quite a lot. So at the end you arrive to the local equation. So the equation which I presented, there is no rigorous derivation of this. I put Dirac mass just to not to have convolutions. So wherever you have Dirac mass, you have to have convolution V, convolution with a psi square, absolute value of psi square.
And in that case, you have results for this derivation. Like if
Sorry?
you have so if you have a very regular V, like localized, you have like rigorous results, or it's still also like the derivation of the.
There are partial results
Mm.
by Grolakis and Macedon.
So actually, I had another question. So about this two gas model, right? I
Yes.
don't know if you want to go back to the slides, but so you introduce this alpha. I mean, these people introduce the alpha, but then you say, neglecting the alpha. So I kind of missed, like, what's really like the role of the alpha.
Okay, so
Another sudden correlation to getting there.
yeah. Okay, so this is not so simple to explain. So the thing is that so what I was talking about is these equations are used for two different in the different contexts. In Bose-Einstein condensation, right? So in a trap, you have confining potential. This is supposed to be a new form of matter. And part of this condensate is supposed to be superfluid. And this superfluid is described by this alpha. But this is small part and you can neglect it. Right? So then you can look at also at when there's no potential and just superfluidity itself. No, this is all phenomenon discovered at the beginning of the 20th century, that at low temperatures, you have the materials, you have fluidity without dissipation. Right? And so obviously this part will play a more important role, or crucial role.
The alpha, you mean that?
Alpha will be important. But when I was talking about this collapse and oscillation around the collapse and two gas models, these are referred to numerical simulations. This was entirely performed for the Bose-Einstein condensate or BEC. Because when BEC was discovered, I don't remember when, maybe 20 years ago, there was the whole explosion of the work, understanding theoretically or numerically understanding the experiments. Right? So all papers, mostly it's numerical work, and it always starts with the comparing with the experiment. So there's lots of this work. And there's this alpha is less important. So it's not, if you want probably to go to the higher order, some kind of a higher order effects, then probably you have to include alpha. But on the level which I was describing, you don't need it. And it's simpler. And you see the original Hartree-Fock-Bogoliubov system is not Hamiltonian system. This is surprising. You have conserved energy, conserved number of particles, but it's not Hamiltonian. And there's no, in the original system, there is no 100% condensation. You cannot achieve the full condensation. At zero, you take a zero temperature and there will be part of the system will be always a non-condensate, will be non-condensate because of the quantum fluctuations, not thermal fluctuations, but quantum fluctuations.
But if you neglect the alpha, then you get this nice. If you neglect the alpha, then you get this nicer Hamiltonian system. Like this
Without alpha is much, well, alpha is, if you throw out this so-called 0-point fluctuation, quantum fluctuations, it will be Hamiltonian with alpha, And then it becomes simpler because in principle you have if in the full equation you have no solutions with alpha is equal to 0 or alpha and gamma is equal to 0. So in other words, you cannot have a solution which is phi gamma is equal to 0 and alpha is equal to 0. They're all coupled. You start with the alpha and gamma is equal to 0, and they're produced by the equations, by evolution. However, if you drop alpha in Duca's model, you have a solution for only phi or only gamma, only Hartree-Fock, only. Yes.
Mm-hmm. Sure.
But I must make maybe I should mention that though we are used in the classical physics, we're used to single equations like Boltzmann equations, like the Navier-Stokes and Euler equations. In fact, we always neglect the second equation. Because if you think about derivation, we neglect infinite number of degrees of freedom, which we think are not important. It's essentially, we essentially make some kind of unstable central manifold approximation. Right? We throw out lots of stuff from the system which plays important role. So in Navier-Stokes equation, we replace all these things by dissipation. But of course, this is just effective description. You have a second system which provides this dissipation. Mm-hmm. So having two equations is really in a case of the effective equations, right? Not basic equations, but effective equations is a very natural and very and physically it's very important.
Yes. Do we have more questions? Maybe before I ask more.
I think it was a long time.
Yeah, maybe we can thank Michael again, and then if there are more questions, we can stay if you have time, but at least to thank him again once more.
Right. You're welcome. Thank you for your attention.
Everyone back next week. Importantly, at 2 p.m., right? Not at 3. Correct. So it's a special time, still on Thursday, but at 2 next week. Then we'll Zoom again at 3 in 2 weeks.
So
the same link though, same Zoom Zoom meeting, same password, etc. Just 1 hour earlier.
So at some point, we would like to have a talk by Gang Zhang. So he's he is one of the people here, and I see him in a little icon window, and but his recent work did not fit. He did lots of work recently on geometry, on mean curvature flow and stuff. So it didn't fit into the subject matter. So
yeah, I'm trying to submit a new paper in this week. Okay, yeah.
Your collaborations are too wide to include like all aspects.
Yeah.
Right. So next week,
the other things to include what could be the work on by my former 2 postdocs on Wojciech and Yaksic and Claude Allaire